understand anything, just bear with me. I can't change my handwriting in 1 hour. Can we remove? Sorry? We can use, I'll in fact show you how AI can be used, or ML can be used. Can we just get rid of this? Okay, so let's say if I were to draw a circle, my circle might look like this, right? But let's say if I want to draw a perfect circle, I just drew till here, I stopped. And so this is a iPad feature. So this is indeed using things like machine learning to draw perfect circles. You can do that. Okay, so we come back to Bayes rule. And we write this in the context of machine learning directly without going into the general Bayes rule. Probability of theta given D. What is this term called? The posterior. Why is it called posterior? Behind. You have seen the data, and post observing the data, D given theta. What is D given theta? The likelihood. How likely is the data given the parameters theta times P of theta? What is P of theta? Prior. And P of D is marginal likelihood of the evidence. So we call this prior likelihood posterior. We will not talk much about P of D. As I mentioned, it can be hard to calculate P of D in various problems, right? So now we have seen for the coin toss problem, we are given a data set of heads, tails, so on and so forth, right? Our problem is, to probability of heads equal to question mark, right? We're trying to estimate this. In machine learning, whenever we're trying to estimate something, we're trying to find out something, we denote it with certain parameters, which we try to learn. So we'll say that probability of heads equal to theta, which means that probability of tails equal to 1 minus theta, right? So based on this, if we look at the Bernoulli distribution, this is Bernoulli distributed, right? So if we have to write that probability that D1 is equal to heads, right? That is just theta. Probability of D1 equal to tails is 1 minus theta. Probability of, so I'm just breaking down the Bernoulli likelihood. Probability of D1 is equal to, we can right, so we can write probability of D1 equal to X is equal to theta to the power X times 1 minus theta to the power minus 1 minus X, right? That's one way you can directly write that what is the probability of seeing this particular data instance, right? So just using this formula for now, or you can write it this way. P of D1 equal to X is equal to theta if X equal to 1 or heads, 1 minus theta, X equal to 0 or tails, right? So both these expressions which we have written thus far are equivalent. Does everyone agree with this? They're equivalent expressions. Now, given the question of probability of data given theta is unknown, right? But let's just fix the data for now. Let's just do the whole calculation. Head, heads, tails, tails, heads, right? If this is the data set, so we're trying to figure out P of D given theta. Since the data is what? We can factorize this. We can factorize this into a simpler expression because of what property of IID. So we can write this as D1 given theta times D2 given theta, D5 given theta, right? Now D1 is heads. We go back. What is probability of D1 equal to heads? Theta. theta times what is probability of D2 given heads? D2 is heads, right? Probability of a heads is theta into theta into tails 1 minus theta into tails 1 minus theta into heads theta equal to theta cube 1 minus theta squared is equal to theta number of heads 1 minus theta total number of tosses minus number of. Does everyone agree with this till now? Right. So we have calculated the likelihood, which is a function of theta. Right. Now, what kind of a function is this? If we were to plot P of D given theta and theta. Firstly, what is the range of theta? Theta is representing probability of hits. So the limits are 0 to 1, right? Now we've observed 3 heads, 2 tails, right? So this function will look something like this then. Right, something like this. It becomes maximum at 0.6, right? Now, this point is where the likelihood is maximized. And correspondingly, theta is known as theta hat, maximum likelihood estimate, right? And what we're saying is that, any questions till now? Any questions from the online audience? So what we're saying is that argmax of theta of P of D of theta, right? So you're finding out that theta, which maximizes the likelihood. This is known as theta hat MLE, right? Maximum likelihood estimate. Find out the estimate for theta, which maximizes the likelihood, right? Likelihood is the probability of observing the data set given the parameters theta, right? And we can also write this as argmin of theta of minus P of D of theta, right? We've just changed the plus to the minus, therefore the function will be opposite. So if this is P of D of theta, correspondingly P of D of theta negative would look something like the following. So now we're trying to minimize, right? So theta at MLE is argmin of negative likelihood, right? But we can also write this as argmin of theta of minus log of P of D of theta, right? Why can we write it this way? Why can we write argmin of negative log likelihood? Because log is monotonically increasing function. Does someone want to explain what do you understand by log is monotonically increasing function? If anyone has a doubt, I would like to address that. Yes. Should we say answer? Okay. Yes. Okay. Yes. Ask such questions. Don't shy. So you're trying to find out that theta corresponding to the maximum. So the maximum is, right, this particular value is the maximum. What theta does this correspond to? So what argument maximizes this function? Right? The argument of the function is theta, right? This is the function of theta. It's important to write. So likelihood is equal to some function of theta, right? Find out that value of theta which maximizes that function. Right? Okay, so let me actually just take this as a appendix. If f of theta is theta minus 2 whole squared, how do we plot this function? This is the function. What is minimum of f of theta? 0. What is argmin of f of theta? 2. What is that value which minimizes this function? So that's the argument. Similarly, if we go back to this plot, what is the value of theta which maximizes the likelihood function? Correspondingly, what is the value of theta which minimizes the negative likelihood, right? And since log is monotonically increasing function, we can write that theta at MLE is argmin of minus log of likelihood. Questions on this? Or in short, we can just write that theta hat is argmin for theta of negative log likelihood of theta. We generally write this as negative log likelihood NLL of theta, right? And this is the same thing as writing argmin of j of theta, right? Where j of theta is your cost function you are trying to minimize. Right? Does everyone follow till now? Any questions? Yes. How is it coming as? Okay. So the question is, why is probability of D1 equal to heads coming as theta, right? So so in this particular expression that we have written, so we have already written, like we make this assumption, right? So given. Yes. So the question is, why is probability of D1 given theta equal to theta? Okay. Does anyone in this audience want to answer that? Why is probability of D1 given theta as theta? So that's just the way we have defined this expression, right? Probability of heads is theta. Probability of tails is 1 minus theta. This is as per the definition that we have given. Since D1 equal to heads, probability of D1 equal to H means just the probability of heads, which is theta. It's a bit of a circular, you can get a bit of a circular argument. But if you just think of it simply, what is the probability of getting a head? How did we define that? We had defined it as theta. D1 is equal to head. What is the probability that D1 was head, or any observation was head for that matter, right? So that is theta. Right? So here, given theta is slightly confusing. Think of it as the theta is already, you know that that's the probability of getting a heads. Given that theta represents probability of getting heads, what is the probability of the first observation or any observation being a head? That's just what is the probability of getting a head. Still not getting it? Okay. Other questions? Any questions from the online audience? So this is a fundamental thing which I want you to remember. The theta at MLE is equal to argmin of j of theta, which is a cost function, is the same as the argmin of negative log likelihood. We can use this to get any loss function in different kinds of problems. So we come back to the question. So is everyone now clear on the calculations? There were some doubts earlier. Some of you had asked that if I could repeat the calculations. Yes, everyone clear on that? Yes. So now the question is, if data set equal to heads, 10 heads, 0 tails, theta hat MAD is equal to number of heads divided by number of tosses equal to 1. right? We obtain theta at ML equal to 1, but is this a good estimate? Probably not. One, we have a very small data set, so we can't say that the probability of heads is 1. We will definitely have to say that the MLE value of theta is indeed 1. Right? Given this data set of 10 heads, what is the most likely explanation of theta? It is probability of heads equal to 1. Right? That is what you can incorporate. That is what you can write. But we go back to Bayes' rule. Let me write it again. Right? So this likelihood is some function of theta, right? Is, let's call it f1 of theta, and posterior, you can also call this some another function of theta. Right? So there are two different functions of theta. If we maximize, or so we're now trying to get a different, better estimate for the parameters theta, for the probability of heads. Right? So one way we can do that is theta hat MLE is equal to argmax over theta of P of D given theta. Sorry, D given theta. Similarly, we have another estimate called maximum A posteriori. Which is the argmax over theta of P of theta given D. Right? So I've just defined these two terms. I believe everyone understands now theta hat MLE now by this time. Now we want another term, theta hat map, which is the argmax of theta argmax of P of theta given D. Right? Now, how do you think we can calculate this, and what other terms do we think we need to be able to calculate this term? Sorry, we need a prior, right? So can you again remind all of us that what you understand by a prior? What is meant by a prior? What is the word, literal meaning of the word prior in the English? Before, earlier, right? Prior to this event, I had done something. Post this event, I had done something. So prior, post, likelihood, right? So what do you think can be a prior P of theta for this coin toss problem? So theta, we said, we are saying theta, we are indicating that as probability of heads, right? What kind of a prior for probability of heads can we give? Uniform distribution between what and what? So probability of heads, right? Theta or probability of heads, right? That is limited between 0 and 1. Right? You cannot have probability greater than 1 in this particular case, right? So one such distribution is this particular distribution. Is a uniform distribution, right? So what does this tell us? Can someone in the audience tell us? What do you understand by this particular diagram? Sorry? So the prior is a distribution, firstly. A distribution. So the prior is a distribution of what? Over what parameter? Theta, right? So let's go over these terms again. Prior is a distribution over theta. Likelihood is a function of theta, not a distribution over theta. And posterior is also a distribution over theta. We'll come to the specifics in a minute. But P of theta is telling you that what is the likely values of theta, right? So you're saying that theta is uniformly distributed, right? Theta being uniformly distributed means that theta could have taken any value here. Theta could have taken this value, or each of these values between 0 and 1 is equally likely, right? Which means that you don't know much about the problem. So were you able to see? Okay. Yes. So each value of theta here seems to be equally likely between 0 and 1. You don't know much about the problem. But we could have chosen another distribution. Ignore the height for now. I just skipped the height just to keep things simple. 0 and 1. 0.5. All of the mass is at 0.5. So what is this distribution called? Yeah, Dirac delta or delta distribution. All of the mass is at a single point. Now, you can say that if you have this kind of a prior, you're saying that I am very, very sure that the coin is unbiased. You have a strong prior, you have a strong evidence that the coin is indeed unbiased, right? And you place all of your mass, all of your beliefs in it. In fact, this is a very limiting case in the sense that you won't be able to, even if you collect more data, your prior beliefs won't change because you're using the delta distribution. I'll not go into the details. So these are two different ways we have seen, right? But we could have chosen some other prior, which looks like the following, right? So what do you understand by this prior? What do you think this prior is encoding? So this is indicating that probability of heads is high. Right? Generally, the probability of heads is higher than the probability of tails, because if this is 0.5, you have a lot of mass right to 0.5. So this is indicating that the probability of heads is more. Right? So again, think of this as this setting that you have some notion of this coin being a biased coin, and you know that it's much more likely to turn up as heads than as tails. Right? This is the prior knowledge that you already have some access to, right? So now you need some way to be able to create this kind of a distribution, uniform distribution, the delta distribution, this kind of a distribution, right? So has anyone here heard of the beta distribution? Again, is this something you've heard, solved problems in the mathematics class, but didn't find it useful? Yes. Okay. So now let's look at the beta distribution. I'll move on to my slides. So you need a distribution which gives you which has support between 0 and 1, right? Which won't give any values greater than 1 and lesser than 0, right? So one such distribution is the beta distribution. So why don't you think we could have used a normal distribution here? Could we have used a yes? No. So this is one specific parameterization. You could have also chosen probability of theta given mu and sigma. That's the parameters of the normal distribution. Why don't we use a normal distribution sorry? Right. The normal distribution has infinite support, right? So you can when you draw samples from a normal distribution, given a mean mu and scale sigma, you can draw samples which are minus infinity and plus infinity, although they are very unlikely, but they are possible. So this is known as the support, the range of values that you can sample, that you can get from the distribution, right? But here you want the probability of theta is representing the probability of heads. You want that to be a number between 0 and 1, right? Therefore, you need a distribution which is parameterized between 0 and 1. You don't need to write the formula. Don't worry about that. So let's just look at some instantiations of this distribution, right? So in the plot, you can see on the left hand side, you can see P of theta, right? This is the probability distribution similar to what I was showing earlier. And the x-axis is the random variable theta, right? So let's vary the two parameters that we have here in this distribution. Let's see if we had kept it. Okay, so let's say we had parameters like this. What do you think is the prior information now encoded? What are we basically saying through this? That the heads is much more likely or less likely than tails? Much more likely. What if we had something like, now what do you think is this distribution? This is uniform distribution. So we're just varying the parameters of this distribution. By keeping alpha beta equal to 1 and 1, we get the uniform distribution. Now let's look at some other parameters. They are two parameters of this beta distribution. So beta is parameterized by this. We'll come to, so in a few minutes, we'll see what some rough analog of what alpha and beta could mean. In fact, we'll see it in just 2 minutes. We'll see. So if alpha and beta both 2, so what do you think this distribution is now telling you? Sorry? We won't say equally likely. We say that there is a high probability that the probability of heads can be 0.5, right? There seems to be high probability that probability of heads can be 0.5. Now let's move from 2 to 3, 3. What do you think has changed? It's become now closer to, right, the variance has reduced and the distribution has got closer to 0.5. Theta equal to 0.5. Did everyone observe that? Let's go one step further from 3, 3 to 4, 4. Has it got even narrower? If you want to see more direct jump, let's go to 10, 10 and see. So carefully look at this 10, 10 distribution, look at the variance, and let's go to 2, 2. Right? Can we see that the variance has significantly reduced, right? So now coming to a question of alpha and beta, you can think of alpha and beta as, let's say you in your head, you had previously thrown some coins. Right? You have not done any experiments in the real world, but you maybe thought that if I had thrown coins, you're basically trying to get the prior distribution. If I'd thrown 20 coins, 10 of them had landed as heads, 10 of them had landed as tails. This is not the part of the data set that you'll be using for computing the likelihood. This is just in your head, right? And you thought that maybe the pseudo counts or the counts that you got were 10 heads, 10 tails, something to that effect. If maybe you assume that it's 10 heads and 2 tails, then the probability of heads is significantly higher, right? So this is not the probability of heads and probability of tails. This is the distribution giving the probability of heads. And these two parameters, you can think of them as, you call them hyperparameters, or you call them the parameters of the prior distribution, right? Just think of them as some pseudo observations that you have, or observations you had before you drawn actual observations, right? If this is getting a little complicated, don't worry. I would say just think that there are two parameters to it. And if the numbers alpha and beta are both large and comparable, then you're saying that probability of heads is equal to 0.5. It's closer to 0.5. If the numbers are closer to 1 and 1, then you're saying that it's more or less like a uniform distribution. Is there any question in the audience, from the online audience, from this audience? Yes. So now coming back to the question of, we had written two estimates. One was theta MLE, the other is theta map, right? Now for calculating theta map, we needed a prior distribution as well as the likelihood. For theta hat MLE, we needed only the likelihood, right? So let's write the Bayes rule again. Right, this is the Bayes rule, right? If we maximize this term, right? What is the theta called? Maximizing the likelihood gives you what theta? Theta hat dash 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 MLE, theta hat maximum likelihood estimate. And if I maximize the theta corresponding to this distribution of this function, what do I get? theta hat map, maximum A posteriori, maximum likelihood estimate, right? But if I have to maximize this term, I have to maximize this whole expression, right? Does the denominator have any term of theta? So for now, we'll just assume it to be constant, right? And not affecting our optimization, right? For instance, just assume P of D is 0.2 or P of D is 4.5, whatever, like it's a density. So let's assume it's any number, but we don't care about it because it's a constant in the case, in our case. So then if we want to maximize P of theta given D, which it means that we want to maximize D given theta times P of D. Right? Does everyone agree? And now I've just, so this is my likelihood. I have H heads and N minus H tails, right? This is continuing from the previous experiment. My data set is small h heads, N minus H tails. My prior P of theta, I'm keeping as the beta distribution, right? There's a bunch of complicated maths. There are some constants, but you don't need to worry about anything. All you can need to see is that once I figure out this log of, once I figure out P of theta given D into P of theta, this is the function I want to maximize. Can I also maximize correspondingly its logarithmic? Yes. Why? Because log is a monotonically increasing function. This lecture, you may get monotonically bored by hearing this term again and again, but I want you to take this home. It's a very important aspect. So can we do a log transform of this term, right? Do a bunch of calculations, just simplify things a little bit. And I get theta hat map to be H plus alpha minus 1 divided by N plus alpha minus 1 plus beta minus 1. Right? So previously theta hat MLE was what? H over N. Theta hat map is H plus alpha minus 1 and divided by N plus alpha minus 1 plus beta minus 1. Right? So this is what I was saying, that can you now think of in your head that you had previously thrown alpha plus beta coins when you're discussing about the prior, right? Out of them, alpha landed as heads and beta landed as tails, right? So from the MLE, we had H over N, but for the map, we have something similar, H plus some notion of prior heads divided by N plus some notion of the total number of prior tosses, right? Any questions in this? This is a relatively hard topic. To be. So alpha and beta uniform means alpha is 1 and beta is 1. So what do you get if you put? So what do you get? Yes, good question. What happens if you choose alpha equal to 1 and beta equal to 1? Sorry. So for a uniform distribution, on the prior, theta hat map is equal to what? Theta hat MLE. Why do you get that? This is an important observation. Very good observation. Yes. Uniform distributions in this specific case means we have nothing which the prior is adding, right? We have absolutely no notion of the parameter values from the prior. So in that case, everything is going to be dominated by the data, which is the likelihood term. Right? Do you get it? So we can derive this in multiple ways. One, we have seen a specific example, but otherwise we could have also seen in this regard, like if P of theta is uniform, then you're not getting any specific term from it. So like P of theta being uniform will be just a constant, right? So we can just write it as a constant. Therefore, it does not appear in this optimization. Therefore, the maximization of the posterior is equal to the maximization of the likelihood if the prior is uniform prior. Yes. Any questions? Any questions from the online audience? So let's run the same example now. Let me actually go back and maybe just define the data set. So just for the purposes of showing that map works, I will change the data set to be 10 heads. Okay. Oh, the MAD, if you put a scatter here. Right, probability of heads is going to be 1. Right, so we have, so if 10 heads in 10 tosses, probability of heads is equal to be 1. And then if we go to theta is 1.4 here. So clearly there's something wrong in the code. Okay, theta keeps increasing. Why do you think this is happening? Sorry. Yeah, but theta should be constrained to be 1. Yes. Why do you think this is happening?
Because we are not considering the probability of the data, the denominator part.
Sorry, just one second. Let me answer. Sorry, can you please repeat the online person?
So in considering value of theta, we have not considered probability of the data only. The denominator part in the base. That might be the reason.
I'm having a hard time understanding because of the volume is probably a little low. So we have, so in this case, we're just looking at the maximum likelihood estimate, right? And we've just considered the data. We have a loss function, which we are trying to maximize. So I think this is behaving like an ill-behaved loss function, right? So indeed, in this case, if you see this curve, right, it seems to be a function which is going continually up, right? If you're trying to maximize a function like this, you'll have theta which is greater than 1, right? So, but we want theta to be constrained to the 0-1 space, right? So there are some tricks which we use here. Instead of using probabilities, we end up using something known as logits, right? I'm not going to go into the that specific practical aspect here, but this is solvable via a couple of lines of code. We could have fixed that, right? I want you to think about this. In this case, the function is going to be maximized beyond theta equal to 1, right? But we want to somehow constrain theta to be between 0 and 1. So that's the problem with the current way this specific loop is written for finding out, for this gradient descent operation is being written, right? So nowhere in this routine have you said that you want the number to be constrained between 0 and 1, right? You want theta to be constrained between 0 and 1, right? But have you already studied something which helps you to constrain numbers between 0 and 1? Sigmoid, right? How do you plan to use sigmoid? Yes. So sigmoid of theta. So sigmoid of theta is between 0 and 1. And if you take the inverse of sigmoid of theta, that will be between what and what. So you want a theta. So whenever you're solving gradient descent like operations, you want to work in the unconstrained space, which unconstrained means that theta can be from -∞ to infinity generally, right? But here theta has to be between 0 and 1. So that's where you have the logit function and the inverse of it, which is a sigmoid function. So you don't learn theta, you learn the logit of theta, you applied sigmoid over it, and then you solve this problem. So I probably said a bunch of things. I just want you to maybe just note down these two terms: logit, sigmoid, and just parameterize Bernoulli with, instead of probs equal to theta, just parameterize with logits. If you just know these three things, you'll be able to modify this loss function, which hopefully should then work out better. I mean, is that correct? Sorry? So it's very good. Now you folks have already discovered a bunch of things which will help you to understand these concepts even better. But let's come back to the beta distribution now. And now theta map comes out to be 0.91, right? This is based on number of heads plus alpha minus 1 divided by total number of tosses plus alpha plus beta minus 2, right? So this is now not 1, right? Why is this the case? Why is this not 1? Because we had chosen alpha equal to 1 and beta equal to 2, which means that we had some prior knowledge that alpha and beta are not, that there is some prior information. You can't place all the weights on the, so let's see what alpha equal to 1 and beta equal to 2 mean. Alpha equal to 1, beta equal to 2 means that the probability of heads is quite low, probability of tails is higher, but in the data we are seeing all heads, right? Therefore the probability of heads will get reduced in the posterior theta at map, right? You had a prior which said that most probably the probability of heads is very low. You had data which was all heads, therefore you'll have the posterior which will have a slightly lesser probability of heads compared to 1. Right? Does everyone get this? Any questions? Any questions from the online audience? Yes. Diminish. Yes. So it's very good observation that as we increase the size of the data set, prior starts having lesser and lesser effect. Why do you think that's the case? Does anyone else want to try and answer this?
Because there is so much from the data itself we can learn instead of waiting for the prior or any assumption we need to make, because there is so much data.
Yes. So if you have a lot of data, then your prior beliefs should be changed, right? We should be using data-driven methods in that case rather than looking at a prior observations. Excellent. And you can also solve this problem very neatly using optimization. So I just showed the analytical solution, but as we've been seeing, so we create this loss function. So previously we called the loss function as what? Negative log likelihood, right? Now we'll call it the negative log joint, right? Why is it called the log joint? It has the prior as well as the likelihood, right? It's a joint. So we define the negative log likelihood and we also get the negative log prior, right? We add both of these things down, these two terms, we get the negative log joint, which is the new cost function, which we will optimize here. So now can you tell me that does P of theta, does the prior act as some kind of a regularizer? Yes. So what does regularization mean? Can you remind us? Regularization means you want to prevent overfitting, right? How do you prevent overfitting? By putting penalties on what? Weights. What kind of penalties? So in fact, Ashish was talking about an example, and I fortunately had a demo prepared on that already in my course. I can just show this. So we're looking at ridge regression. The left one is the unregularized plot. The right one is the regularized fit, right? Now let me make the model more complex. How do I make the model more complex? By increasing the degree of the model so let's look at a degree 12 polynomial. On the left hand side is the regularized, unregularized function. On the right hand side is the regularized function. It already seems to be smoother, right? It's not trying to fit each and every training data point. Let's not take it to the extreme. So can you see that now the left hand side plot, the RMSE on the trained data set is reducing, right? Because you're trying to fit each and every data point very nicely. Let's take it to the last point that I have, 40, right? And now let's see if we increase the regularization. So this, as we increase the regularization, the lambda, this is the lambda coefficient. The left hand side is remaining unchanged. So now is the right hand side plot just straight line, right? Because we've removed all complexity from the model, you have made all the thetas really small. Individual theta is really small, right? Yes. Sorry, I didn't get your question. Yes. Yes. It is not. Yes. Yes. So what should we do then? Yes. There's no point. We should not be using such high regularization, which means that we should be choosing an appropriate value of lambda. How do you do that? Hyper parameter tuning, right? We should be using hyper parameter tuning, right? Now, we have seen that choosing a regularizer or adding penalty reduces overfitting, right? Let's come back to the coin toss problem now. So in the coin toss problem, what is the notion of overfitting? Sorry? In the coin toss problem, what is the notion of overfitting? Sorry? So the notion of overfitting is that you're placing all of your belief on the limited data set that you have, right? So therefore, in that specific instance that you see here, if you had 10 heads in 10 tosses, you say that my probability of heads is 1. You've placed all of your confidence, all of your beliefs in just the data set. Therefore, you're overfitting to the data set, right? So when we say overfitting, we mean overfitting to this specific data set, right? Once you've overfit to the data set, you need some notion of regularization, right? Which makes, which ensures that you have more generalizability, right? You're not dependent totally on the data. So you have another term which is also there in the loss function, right?
So there is a question from online audience.
Okay.
That over regularization would result in underfitting.
Over regularization would result in underfitting. Okay. Okay, let me ask this question first to this audience. Will over regularization lead to underfitting? So the model is can everyone see? So we had J of theta is equal to negative log likelihood of theta, right? Plus lambda times some function of theta. Generally, function of theta is theta transpose theta, or the L1 norm of theta, right? So does firstly everyone understand that what do you mean by theta transpose theta? No? Okay. So if our parameters are theta, we generally write them as in a form of a vector, right? So we want to say that minimize J of theta such that theta naught square plus theta 1 squared plus theta m squared is a small number. So I'll say that it's lesser than some delta squared, right? It's a small number, it's a non-negative number. This is equivalent to saying minimize J of theta plus lambda times theta naught squared plus theta 1 squared till theta m squared, right? So does everyone agree that we can say that both of these terms are equivalent, right? So this is actually not a very trivial concept. This is, you get this via some conditions known as KKT conditions. And you don't need to know about any of those. But all you're saying is that this is your cost function, regularized cost function. But instead, I generally write it as theta transpose theta. So that comes from the fact that if I can write this again, if theta equal to theta naught till theta m, theta transpose is then theta naught theta m, and theta transpose theta. So theta is m rows, one column. Theta transpose is one row, m column. You want a scalar, right? You don't want a vector, you don't want a matrix. So therefore, you write theta transpose theta. That will be theta naught into theta naught plus theta 1 into theta 1 plus theta 2 into theta 2 plus theta m into theta m, right? Therefore, theta transpose theta is summation theta I squared. Does everyone follow this? Right. So now this is the way you can reduce so you put some penalty to reduce overfitting, right? You're trying to make thetas in this case, when you put a constraint like this, you're trying to make thetas slightly smaller, right? Which will ensure that you don't get those complex wiggly lines that I'd shown in the demo, right? So what I'm saying is that we had seen theta hat MAD equal to argmin of negative log likelihood, right? Does everyone agree with this? This is argmin of negative of logarithmic of this term, right? Similarly, we can write theta at map argmin over theta negative log likelihood plus negative log prior of theta, right? Can we write it this way, right? Which is the same as when we were doing regularized logistic or linear regression. Argmin of theta of j of theta plus lambda times theta transpose theta or lambda times the L1 norm of theta. I haven't shown the specific derivation, but I'm trying to show the relationship between the Bayesian view and the frequentist view in which we are getting regularization in both the ways, right? In one, so in the slides which Ashish had shared, or the notes that Ashish had shared, you had specifically started with this form, right? You want to reduce overfitting by putting some penalty on the parameters becoming very large, right? The same thing you're getting in the Bayesian setting while maximizing the posteriority, right? You're finding the theta parameters which maximize the posteriority, which takes the data into consideration, right? And it takes the prior into consideration, right? If you were to fix, if you look only at the data, you will overfit to the data, right? But if you also, in addition, look at another term, you will not be able to fit to the data as well as otherwise you would have done. Yes, any questions in this? Yes, if you remove the prior, it's unregularized, or if you make the prior uniform, theta map is same as theta MLE. So I want to take some questions now. I want you to think, is there anything difficult? Is there anything we can make simpler for you? Yes. So I mean, this is for a specific form that I'm showing. So this particular thing comes when P of theta is given as normal with some mean and some. So this comes when P of theta is normally distributed with mean mu and sigma as the scale. This regularization comes when we assume the prior is distributed with the Laplacian distribution. Which one? The first one is L2, the second one is L1. So L2, L1. Right. So there's a lot of things I've written. We'll come over them. We'll go over them in a few minutes. But I just wanted to have a summary slide which says that you can get regularization in the Bayesian setting by choosing appropriate priors. We have seen one specific example of the coin toss problem. Where we are able to get in the coin toss problem, we are reducing the overfitting by looking at some prior distribution. Yes, any questions till now? Sorry, when did we get? The log prior. So when we wrote theta MLE, so this thing, so firstly this thing should have been d given theta. It's sorry, incorrectly written. I will correct this later. Is that right? Should have been d given theta, right? Right. So d given theta is the likelihood. P of theta is the prior. When you multiply them, you get something proportional to the posterior because you don't consider the denominator. It's independent of the theta parameter, right? You take the log over this. Take the log of the first term, you get log likelihood. Take the log of the second term, you get log prior. And you're trying to now optimize this function. You're trying to maximize log joint, which is log prior plus log likelihood, or you're trying to minimize negative log likelihood plus negative log prior. That's how you're getting these terms. Other questions? Okay, so now we move on to linear regression. And we will view linear regression again from a similar perspective. I see some frowns, but I think you'll be happier once you revise these things. For now, it's a little bit harder. Like I can assure you, it's easier to just tell you that the loss function is squared loss, right? You just find out y hat of I, your prediction, and you calculate the loss, and you're done. Right? It's a bit harder, but that's where the more fun will be eventually. Right? So tell me some problem for linear regression. So let's say we want to predict the, sorry, I can't hear you. Given weight, predict height, very cliched example. Can we predict something else? So given weight, predict height. Okay, let's actually, it's a fun experiment to think about. Yeah, other examples, you think? Sorry? I'm having a very hard time. Salaries given the height. Salaries given the position. So how do you encode the position as a... Okay, salary given age. Yes. So till the time I'm writing, what is the regression problem? How does it vary? How does it differ from a classification problem? In regression, we are trying to predict a continuous variable, right? So the amount of rainfall, let's say the amount of marks, if we assume that we have infinite precision, the so let's take a slightly weird kind of a problem, and I'm asking this because we were previously, so one of my student was unwell a few months back. So he was trying to get his temperature reading, right? He looked at he took the reading from one particular thermal scanner, right? That was showing 98.6 Fahrenheit. He was clearly feeling unwell. But then when he took the reading from the what is that, mercury based thermometer, it came out to be 101 point something. So there was quite a big of a gap between them, right? So let's look at maybe this particular problem. So we are trying to estimate the temperature, and let's say this is the mercury level, right? Now, so when you look at your regular your thermometers, especially the digital ones, you would have seen. So do you get 101.1, 101.2, or do you get 101.1111, 101.1234? So the least count is generally 0.1, right? So let's say if your temperature is 101.16, will it be given as 101.2 or 101.1? Probably 101.2, right? So let's assume that we have some data like this, where there is a relationship between temperature and the mercury level, right? So we have some readings like this, right? So why do you think there is some scatter in the data? Why are they not along a perfectly straight line? Sorry. No, let's think simpler. So let's assume that all of these readings are from this specific room only, and there is no change in the atmospheric pressure. Human error, but let's assume that we are using, like, all of the humans are capable enough to read digital thermometers. Let's assume these are digital thermometers, and there's an inbuilt model which is used here. I answered this a few seconds back. They don't have full accuracy. They have some rounding off, or there could be some observation error. There could be some error between observing the edgy levels and then interpreting them, right? There could be various reasons, but let's assume that there existed like this is the perfect relationship. Again, please don't look at when edgy level is negative and the temperature becomes negative. Let's not go into that zones. So this particular thing, I'm going to be calling F from now on. This is the true functional relationship between temperature and the mercury level, right? And then I have certain deviations. So I'm certain deviations around that F. How do you attribute these deviations to? What do you attribute these deviations to? So observation noise, the human being could be biased. They could maybe, if it's a mercury based thermometer, like it's the analog thermometer, maybe they're not able to accurately look at the reading, right? Or there is some error in the instrument itself, right? Or let's say there are some other sources of error, right? So we call all of these as observation noise, right? So I'll say that temperature is equal to function of so is Hg the correct symbol? Okay. The temperature is a function of Hg, right? Just for simplicity, let's say that it is 4 plus 3 into Hg, right? F. So we can just say that, that's for simplicity, just write F equal to 4 plus 3x, right? This is my x, and this is my y, and this is my f, right? F equal to 4 plus 3x, right? Now, what do you think is the relationship between y and f? How are y and f related? Is y equal to f? Y is a function of f. What kind of a function? Okay, y is f plus some other function. What kind of a function? So we're saying that these deviations that you see, these deviations, right? These are due to human observation or some other kinds of observation errors, right? So these are errors, right? We cannot directly model them. We cannot, if we could model them, we could have included them in our f function itself. That's the basic assumption that we'll take. So then what do we write y as? How are y and f related? What do you think? Y equal to, okay, let me tell you, y equal to f plus something. F plus noise. What kind of noise? Sorry? Deviations. Yes, they f plus deviations, but then you need to write deviations as something mathematical. Okay, one at a time. Yes. Sine? Sine SIGN or SIN? Okay. So he's saying that it's some sinusoidal function which fluctuates between 0 and 1. Yeah, that's perfectly valid. One way you could have written, but we generally write this as something simpler, something which makes the maths more
Gaussian.
normal distribution. Yes. So we end up writing y equal to f plus epsilon, right? Epsilon is the noises. Epsilon is normally distributed with mean 0 and some scale sigma, some standard deviation sigma. Right? For now, for simplicity, we can just assume it's sigma equal to 1. Right? Can you wrap your head around this? Does this make sense or no? Or does it look like too much of a leap? Right? We are given a true relationship f, right? In this case, it's 4 plus 3 into x. But we have some observation errors. So we don't observe f, we observe y. Corresponding to each x, we observe a y. And this x and y pair become a part of a training data set, right? So we given x and y, we're trying to learn the parameters of this. We never given f, right? Just to make the whole process easier and for us to be able to derive certain things, we write y equal to f plus epsilon, where epsilon is normally distributed with mean 0 and the scale sigma. Right? So why do you think I've written normally distributed with mean 0 and scale sigma, not mean 5 and scale sigma? Could I have written that? No, the scale is shifted, mean is shifted. So 0 means the mean, scale is the sigma. Okay. So the question, I'll repeat the question. Why don't we write y equal to f plus epsilon, and epsilon is normally distributed with mean 5 and scale sigma? We generally don't write it that way because then we could have incorporated that 5 into the f itself, right? Into the function itself. But for now, just for simplicity, let's assume that y equal to f plus sigma, epsilon is normally distributed with mean 0 and scale sigma, right? So we also call this process as a generative process. Does anyone know why? You want to answer? Why do you think this is a generative process? We are trying to generate data. So think of it as, now you're given x, right? Given x, let me write the entire thing. Yeah. So given x, we can calculate f equal to 4 plus 3x, f of x, calculate y corresponding to x equal to f of x plus epsilon. But even to calculate epsilon, we need to get epsilon is normally distributed with mean 0 and this. So we get a sample from here. We get a sample from the normal distribution with mean 0 and scale sigma. Maybe that comes out to be 0.3, or it comes out to be another iteration comes out to be minus 0.6, right? So then we can write yx equal to fx plus epsilon. Right? So in this process, we are generating the data set. Right? This is the generative view of the problem. So we'll come back to the notebook now. Right? This is the exact same thing I was writing earlier, and I'm showing in code. So X is linear space values between -1 and 1, and there are 10 values. That's what linspace does. Actually, let me just show you in case you're unsure. X is 10 evenly spaced values between -1 and 1. 11 is a better value here because it just makes the numbers easier to view. So you have 11 evenly spaced values between -1 and 1. These are your X values. You have the real slope 3, the real intercept 4. So your F is equal to, I had been writing this earlier also, F is equal to 4 plus 3x, right? That's what I've written. Noise scale is 1.0. My likelihood distribution is a normal distribution with location equal to F plus scale equal to, right? Actually, I can write my epsilon is normal distribution with location equal to 0.0, scale equal to noise scale, and my y is equal to f plus x, right? Actually, I directly can't write it here because I need to get some samples from the normal distributions, because f is values, so epsilon is a distribution, so we can't directly write it this way, but that's how we would have f plus, sorry, not x, epsilon dot sample. So we'll write something like this, right? I'm not showing that here, that's already being done here. Right, so now let's see some samples drawn from this distribution, right? So you had, so in fact, there's another important detail to it. So I'll have to write this again. F is equal to 4 plus 3x. And epsilon is normally distributed with mean 0 and scale sigma. Okay. So f is equal to 4 plus 3x. Epsilon is normally distributed with mean 0 and variance sigma squared. So actually, we would not directly write this as f plus epsilon. This in some sense is wrong, because epsilon is a distribution and f is values, right? So we actually want to write the more correct way to write this would be y is normally distributed with mean f, right, at x, and sorry, not epsilon, and scale sigma. Now this is an important statement. Do you agree with this or don't agree with this? I mean, for a given x, that's why I've written. So let's think of it this way. So the other way to look at this is, let's have x and we have y, right? So let's maybe pick up at x equal to 1. What is the value of f? 3 plus 4x. 3 plus 4x, so 4 plus 3x. So it's 7, right? So we have f equal to 7. At x equal to 2, we have f equal to 4 plus 3 into 2, 6 plus 4, 10. 7 and 10. right? Let's just assume that we have more points, something like this, right? So this becomes our F, right? Now what we're saying is, and this is the most important aspect of this particular set of slides. I'll in fact have to rotate my thing to draw. So what we say is that Y is normally distributed with mean F of X and the scale as sigma. So I rotate my screen and I draw a normal distribution here, right? Similarly, at this point, my mean is F of X, my scale is sigma. Maybe at some other point, again, I have a full distribution of values I could have picked up from, right? So these are the full distributions. Now, if we had chosen one particular random seed to draw the samples, maybe the samples which we get are this, 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 right? Does everyone follow? So maybe I should just use different colors. Right, so blue color here is indicating F, right? The green color is showing the Y distribution at corresponding to an X, right? There's a bit of abusive notation, and this is a sample from Y of X, right? This is one specific sample that you could have got. But what's also likely is that you could have maybe picked up, because it's a normal distribution, you're trying to sample from a normal distribution. Maybe you could have picked up this sample, this sample, this sample. This is another sample. Horrible choice of color, but just bear with me. So you could have chosen another sample this way, right? But the important central theme here is that F is a function of, it's a linear function in the parameters, right? So F is 4 plus 3x. The observation noise is normally distributed as mean 0 and scale sigma, right? This is the deviation that you get. This is the deviation that you're getting at each point, right? So we're saying that each of this epsilon i's that you're getting at corresponding to a corresponding xi is normally distributed with mean 0 and scale sigma. And therefore, we can also write y to be normally distributed with mean f and the scale sigma, right? So think of it as you're adding this and this. The first one is a deterministic function. The second one is a distribution, right? Therefore, this thing comes in the mean. And so think of it as this equal to this plus this. And the variance, because this thing doesn't have any variance, it's deterministic. So the variance here is directly coming from here, whereas this plus this comes here, right? Therefore, we can draw something like this. First, let's go slow. We fix x, we get the f. F is a deterministic function. In this case, it's 4 plus 3x. At each f of x, right, we can draw a normal distribution. So y is normally distributed with mean fx and scale sigma. And then when we're trying to get some samples from it, we could have got a sample like this, or we could have got another sample like the yellow one. So the red and the yellow are two different samples you could have got from this same underlying process, right? So coming back to the example, X could be your mercury levels, right? And let's say there are two different set of people who are, or let's say you're looking at the mercury readings at two different points of time, or two different set of people are looking at it, right? So there could be some observation noise between them. One of them ends up thinking it's the yellow one, the other one ends up thinking it's the red one, right? but none of them are able to accurately get the blue one. If you'd got zero observation noise, then it would have been a straight line directly. Any questions, online audience, physical audience? The snacks are not far away, so just be there for a few more minutes. Okay, let's shift again to the laptop. So let's now try and look at the same thing as I was showing earlier. You have real slope is 3, real intercept is 4, f equal to real slope into x plus real intercept. So it's 4 plus 3x. And I'm now generating some samples from it. So you could have got any such sample set. You would have got y and x pair, x and y pairs, right? You would never get f. So for one particular random seed, maybe this is the red is the set of observations that you'll see y. For another seed, you could have seen some other different set of observations. Another seed, you could have seen something else. So as I'm just going through the different seeds, you can see that given the same generative process, you could have had various different data sets. Right? Does everyone follow till this point? Okay. So now comes the fun part, which I've been waiting for. So you know so how do we now calculate the likelihood of this data given the parameters theta? First question, what are the parameters theta? So this is a data set that is given to you, right? But that's the true set of values, 4 and 3, right? But now you're given this data set, right? Let's say you're given this x and y data set. I can actually maybe show you. So you have x and corresponding y. Okay. Does this look like a standard machine learning data set that you'll get? You'll get a CSV, you'll get some kind of a data set. You have x and y pairs. Given this data set, you're trying to fit linear regression, right? What are the parameters you use in linear regression? What are the parameters here? Y is equal to what plus what? Y equal to mx plus c, or y equal to theta naught plus theta 1x, right? Can we write it this way? Yes. So then what are our parameters? We have two parameters, theta naught and theta 1, right? And then we're trying to estimate these parameters given the data set. What is the procedure that we've seen to optimize to figure out a set of parameters given a data set? We figure out the loss, but how do we get the loss? Maximize what? The likelihood, right? Now, what is the likelihood of the data given this set of parameters theta? So I'll repeat the question. What is the likelihood of what is the probability of viewing this data, of getting this data given the parameters theta? Let me actually just make it slightly easier for you. I'll again shift. Okay, so let's first fix the setting. Your data set is x1, y1, xn, yn pairs, right? Your parameters theta, theta naught, theta 1, right? Now let's see that if we were to pick some kinds of parameters, right? Let's see if we had picked up. So what is the relationship between y and so I think I should just explicitly write it. We write y hat equal to theta naught plus theta 1 into x, right? So we had chosen theta 1 and theta naught both to be 0, right? Let's maybe plot that in this color. Right? Do you think this is a good model? No? Why do you think that's the case? It's not fitting the data, but what is the notion of fitting the data? Are these set of parameters likely to have produced the data? Is this set of parameters likely to have produced the data? Yes. So what we are trying to do is to figure out a set of parameters theta naught and theta 1 for which the likelihood of the data is maximized, right? So our problem becomes that once we have these parameters theta naught and theta 1, find theta naught theta 1 such that probability of getting the data given the parameters theta is maximized, right? Now data is x1, y1, x2, y2, so on and so forth. We have n data points. What can we assume about the data set? The data is what? Dash, 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 IID, right? Can we then write, we're shooting above time, but don't worry, your snacks won't go anywhere. They'll taste tastier once you've figured this out. Can we write it this way? Can we write the likelihood in this particular fashion?
Yes. Yeah.
Why can we write it this way?
It's IID, right?
IID assumption. So now the only thing you need to figure out in order to solve this particular function. So you're trying to find out this theta at MLE equal to argmax for theta of P of D given theta, right? Now, if you can figure out this particular term, what is the probability of data set observation 1 given theta parameters, then you're solved. Then you have basically figured out this problem. You want to answer? No. So let's break at this point so that your tea coffee break is okay. So there's a good question. Is there any mathematical justification as to why the error is normally distributed? Okay, does anyone want to answer this question? And after that we'll break. Okay, so this is the question why. So one of the answers is that normal distribution is symmetric, right? About the mean, and the mean is 0. So that's one good reason. So there are a bunch of distributions you could have used. One is the student tree distribution. One is, let's say, normal distribution. Normal distribution gives you a lot of leverage. So it's mathematically very convenient to use. And you can justify, you can give a bunch of reasons as to use a normal distribution. It makes the least amount of assumptions to explain a certain amount of variance. But the most important reason is that it occurs in a lot of places naturally, in things like central limit theorem. And the other reason, perhaps the most important reason, is that makes the mathematical calculations very convenient. And for this specific example, we'll see that choosing this particular form will give us the squared error as the loss function, which again seems very natural, and it's a convex function. right? So there are a bunch of reasons why we'll end up using the normal distribution. So let's stop at this slide. We want to maximize this particular function. Now we need to figure out what is probability of data set point 1 given the parameters theta. Theta is theta naught theta 1, right? And d1 is x1 and y1. And we know this functional relationship between y and x. So with all of this, I want you to think, and it will be wonderful if some of you are able to get somewhat of an answer by the time we come back. Okay, we'll break here. Any questions, let me know.